A very good afternoon. This is probably the first talk about, we have listened a lot of talks about different applications. This is probably a talk about core computer science per se. And computer science started when people started writing programs. I mean, at least computers came into existence and people started using them to write applications once we started with programs. And hence, let's have the question of the symposium. I hope all of you write programs. Which programs are the fastest? If I were to ask you just this general question, what would you say? How many of you say C? How many of you say C++? You have to raise your hand. Java? Anybody says Python? Yeah, you should go back and learn about interpreters and compilers if you say Python. But see, nobody raised hand in Java. Everybody thinks C programs are the fastest, is it? Let us have a demo to prove you wrong. Okay, so let's say I have this language war screen over here. I have very faithfully reproduced a program in 4 different programming languages. I have a C program. Basically, I'm taking some user input. Don't look at the computation. I have 3 nested for loops. Each loop is executed the number of times I have taken the command line argument as. So you have 3 level nested for loops like matrix multiplication, some random computation. The same code is reproduced in C++. Here we have objects. I have Java code for the same computation. I don't write Python programs, so I asked a student of mine to write an equivalent Python program for the same as well. And then I have a script. I'll just run the 4 programs with some number of iterations supplied. If I supply 10, each loop will run 10 times. So the inside computation would be 10 times, 10 times, 10 times. Okay. Let's just run this a couple of times and see. Just a sanity check. If I run it with the input value 100, it's running. I'll get some answers that will print how much time did each version took. Python program 0.9 seconds, C 0.6. Java was the fastest, but fine, maybe it's a one-off case. It's just an input size of 100. Let me change it. And since all of you agreed Python programs are probably the slowest among this set of 4 languages, let me just comment out to save time. Okay, let us now make it a bit larger. Let's make it 500. You know, my laptop is not very powerful. Even if you run it on without the Zoom call going on, it will still take nearly half of the times that you see on the screen. So, well, there seems to be some magic going on. Final one. After that, we'll continue with the talk. So, let's see. The C program still runs. Can I walk back till the time C program finishes? Yes, 5 seconds. C++, something similar. And then you would see what happens for Java, 1.7. What is going on here? Java programs seem to be the fastest. Who told C programs are fast? They're even slower than C++ sometimes. Alright, this is just about this program, just to make a point over here which we'll come to later. But keep this point in mind. So what happens? Why are Java programs fast? If you still had memories from some of your older textbooks or something that, okay, Java programs are interpreted, they are very slow, that changed from that has changed in the last 15 to 20 years. When you compile Java code and generate class files, these platform independent class files that you can run on any machine, you have not only an interpreter sitting inside the Java virtual machine, but also few compilers. Okay, that's my research area. So you have something called as just-in-time compilation going on when you execute a Java program inside a VM. If you have code that executes frequently, I have a loop that I am iterating over a large number of times, why to interpret it line by line? I should compile it, optimize the code and run that code. That's how it goes. Okay, so this is just-in-time compilation for you. This compiler 1 and compiler 2 that you see in the diagram, this figure represents Oracle's OpenJDK virtual machine that probably most of us use. And those 2 compilers sitting inside the VM are called just-in-time compilers. So what happens when you run Java programs? Well, it's not only about Java. A lot of object-oriented programming languages per se follow this model. When you run a Java program from the main method, right, from the first statement, you actually start interpreting the bytecode. You start interpreting the bytecode and then you jump over. You find out this piece of code is getting executed frequently. You jump over to a compiler. Well, there are multiple levels of compilation here, 1, 2, 3, 4, where each subsequent level is more powerful in terms of the optimizations done over the program. than the previous level, and your program is essentially traveling across, or different parts of your program are traveling across these different phases as your program executes inside the VM. Okay, there are some grayed out parts over here, and this is a chota demo. Okay. If you print some extra information about the program, you can see some numbers on in the third column, 333, sometimes 4343. It actually tells what part of the method foo is being executed from what level of compiled code. Okay, so as I told you, there are multiple levels of compilation, and those are visible. You can see them. You can understand what part of your program is at what level of compilation while executing your code. Okay. Now, in the hotspot VM, the VM that we, as I said, the Java virtual machine that most of us use, you basically, as I said, start off by interpretation of bytecodes. Then while you execute your program, you also keep recording. Okay, if I see a method call, let me increment a counter. Method foo is called one time. If I call foo somewhere else later, let me increment that counter and make it 2. I see a loop. Every time I iterate over the loop, let me increment a counter. Okay, the loop got executed by one more time. And as you keep incrementing these counts, if you reach a certain threshold, you decide, okay, this piece of code is hot. Hot means frequently executed. You insert it into the compilation queue. There are 2 threads waiting there, one thread for each compiler, that are waiting for code to be fed. Give me code that I can compile. As soon as you insert something into the queue, in parallel, your program has not paused execution. Your program is still executed by the interpreter. In parallel, that thread creates a new compiled version of your code for the machine on which you are executing the program and gives you a performant binary. Now you will switch over to that performant binary. Okay? This is a very dynamic system, and this is how Java programs are executed. Entry points of methods are changed dynamically. Whenever you call foo, you were going here. Now you have the compiled code available loaded in the memory at a certain address. You will change the entry point such that next time the method is called, you will jump to that address instead of interpreting bytecode over here. Okay. Similarly, you may replace loops that are hot on the stack with compiled code. Okay. Then you also see some more stuff there. The gray one is with full profiling. Well, fine. I can compile and count how many times a method is executed, how many times a loop is iterated. Can I count more interesting things? If I can profile a program, I can profile even more interesting stuff, isn't it? So now there is something called as speculative optimizations that are performed inside Java virtual machines, which is completely absent, not possible in C compilers, for example. Okay. Basically, you speculate, you make a guess based on the live runtime profile of a program. For example, I can guess if every time I choose a condition, I can count, okay, 10,000 times, the previous 10,000 times, always the if branch was taken, the then branch was taken, rather the condition was true. So I can just assume that always the if branch is going to, the then branch is going to be taken, and I can remove the else branch. I can optimize code further from that point. Okay, so there are optimizations like this that are done by VMs. Let's take one more example. All of us like seeing code. Yes. So let's say I have this piece of code. There is a method foo which does some computation. It takes 2 parameters A and O. There is a method bar which is called inside foo, and there are 3 implementations of bar. This is an object-oriented program. So which bar is called depends on the type of the object pointed to by O. Okay. Now, if let us say somebody tells me most of the times this method is called, variable A's value is 10. If I make that assumption, I can propagate the constant 10. B would become 10 plus 10 as 20. I can just say int C equals 20 times O dot bar. Now, if somebody tells me about the second argument, that okay, most of the times O's type is Y. What can I do? I can inline the method bar of class Y and replace the call to that method by the return value 2. Finally, I can perform one more round of constant propagation, and my whole method, which had some addition, some multiplication, some method call, some assignment, some variables, everything just got replaced with return 40. I got optimized code, right? This code will run probably faster. It will take fewer resources than the previous original method foo. Right? And this is the binary the JIT compiler will generate, which gives you performance. Now, of course, you might say, if I generated a binary under certain assumptions, what if the next time I call foo, I pass in 20 instead of 10 as the first argument? Can you execute the binary that you generated with the previous assumption anymore? No. So you have to invalidate the code that you compiled under a certain assumption. So we compile and create a specialized binary under certain assumptions. What if the assumptions fail in a subsequent run? We should have some mechanism to fall back, to repair the program while you are executing the program live, right? So when a profile guided assumption fails, you invalidate the compiled method and you have to fall back to some safe path. Well, can you give me an example of a safe path? You had an interpreter and compilers. If compiled code is wrong, is there an option? The interpreter, some of you are moving your lips at least, I can read it. So you can fall back to the interpreter still has the complete bytecode of the method foo. If the assumption was wrong, you can fall back to either a lower level of compiler or interpreter and resume execution. Okay, so this is how programs execute in a JVM. You have these several speculative optimizations, you have this interesting engineering that may move your method from one state to another. In use, not entrant, zombie, these are technical words. Compilers people are the most funny people in the world in computer science, believe me. They use interesting words inside the code they write. So a method can be zombie. If it is zombie, it means that, okay, that method has not, the compiled version has not been called for a long time. I can throw it away when I do garbage collection later. I can reduce the amount of memory consumption inside my VM. Okay. So now let me ask, well, if some of you were thinking, will we talk non-technical or technical stuff, we'll move quickly. But before we move to some advices for PhD students and so on, question of the symposium. Again, the question is, which programs are the fastest? How many of you say C? How many of you say Java? Wrong. Everybody is wrong. It's the compiler that makes programs fast. I can write a better C compiler and make those programs fast. I can write a good Python compiler and improve the performance of Python programs and so on. Remember that at least from my talk. Okay. So this is my research area. All of us write programs, all of us read programs, all of us debug programs, and compilers process programs. They take programs as input. They produce something that's performant. They optimize the code. They can take advantage of the runtime in case of virtual machine-like systems, and they can actually improve on various parameters, not only the performance in terms of speed, but also the memory consumed by your program, the power dissipated by the program. They can actually help you get the green earth goal. People are working on it. It's an active research area. Okay. So when I started, I am from a small town of Madhya Pradesh. I did a direct PhD at IIT Madras, and when I chose compilers as an area, everybody used to say, "Oh, dead area. What will you do? No publications possible." There is a small research area in compilers called pointer analysis. People worked on pointer analysis from 1970s to 2000. In 2001, there was a paper that said, do we still have anything left to do in pointer analysis? That author claimed yes. I wrote a similar paper in 2020 and I asked the same question and the answer is still yes. In every conference related to programming languages, there are 4 or 5 pointer analysis papers every year. So the area is, even one small branch of compilers is not dead. It's a very active research area. If you write liking programs, do not be afraid of working with programs. Okay, so after finishing my PhD, we did some work with Java, R, and so on. I moved to IIT Mandi, where I taught new courses. IIT Mandi is an IIT in the Himalayas. You can see my office was on the top left corner over there. And I offered some new courses over there. I became a popular teacher in some sense. I got some awards there and so on. And then finally, right now, I am back to the central part of the country. I'm at IIT Bombay, where again, this time I am offering a new course on code optimization for O languages. I have a few PhD students who are doing very good and so on. So as you can see, there are few takeaways from this journey, from this short journey that I told you in the previous slide. One is, do not be afraid of taking your decisions. If you like doing something, what I have learned in the last 10 years from the time I started my PhD, do not be afraid of choosing your own path. There is no if you do not know, let's say it's for a PhD and you do not know what should you do, you do not know which area you are interested in, you can try an MS by research program, you can try stuff. It's not like you have to just decide on the day you graduate, okay? Secondly, there is no shortcut to hard work. My first paper, in my area, if you get 3 good papers, your PhD is done. In your whole lifetime, you get maybe 40, 50 papers. That's much less. I mean, each paper's value is more than papers in some other areas. But my first paper I submitted at the end of 3 years of my PhD, and it got accepted at the end of 5.5 years of my PhD. It took 2.5 years to get my first paper accepted. Well, of course, I was doing some other work as well in parallel. It wasn't like I could not graduate on time. I finished in 6 years. It's 2 minutes. So, what I had to remember was, well, no, my guide was very particular. No, you should not submit to conferences that are low grade. You have to target A star. I kept on surviving and so on. And what I learned at the end is there is no shortcut to hard work. I got into IITs as a faculty member, so that patience was worth, right? So that's another thing that you should remember from my life story, my short life story till now. If luck works, well and good. I had a colleague whose paper got rejected in a conference. He submitted the same paper in a journal, he got best paper award. Sorry, vice versa. In a journal it got rejected, in the conference it got the best paper award. So sometimes luck may just work. If it doesn't also, you have learned something on the way. You know at least what may happen. You can tell it to your future students, right? Enjoy the process. Secondly, ends are just an event. Don't look for the day of graduation from the day you start. It's not a 5-year, 6-year journey. If you start a PhD, it's a lifelong, it's just the first step of a lifelong research career, as we say, right? So do not look at the end. There is no end. Once you start doing research, it goes on till the end of your life. And finally, if things are not working out, remember, humans are extremely capable. Life has no limits. Play with these binary computers, but don't forget that life is fuzzy. That's something I like to say. Okay, and finally, if you want to remember from the technical content of my talk, compilers and programming languages are a very active, vibrant and interesting research area for nerds, for theorists, for the practitioner in you, for the engineer, for the scientist, everybody. You would like it. If you like working with programs, please consider joining my research group or any other group that works on compilers and programming languages. Thank you.